My name is Jon Masters. I'm a computer architect with Red Hat. Hands up if any of you have heard of Red Hat recently. Right. I won't be commenting on that, but this is the closest I ever get to a blue suit. So I'd like to thank the organizers for inviting me. After the talk, you can tweet me questions. So take that handle down right there. I'll be answering the questions. We'll just take a group selfie right here. There we go. Very good. So I just have a few slides, maybe 100. We're going to do this very quickly. So put your hand up if you have never heard of these two things. Good, you're in the right room. That's great. Okay, put your hand up if you have never seen all these logos before. Maybe one or two of you have not seen all of these logos, right? So what I want to do today is talk a little bit about this mess that is 2018. Welcome to 2018, everyone. It was an exciting year, wasn't it? Right? Everyone's really super excited about patching their systems every 10 minutes. It's a good thing we've got all the rolling outages prepared for, right? So, no, it was a very special year in the industry, and what I want to do now is talk a bit about how we got here and what it all means, and then what's happening going forward. And I'll be available outside later on today, or you can tweet me with your questions, right? Now, before I get started, and I will caution that these slides did exist prior to yesterday, I'm going to use an example of another architecture to showcase the fact that this is not just x86 specific. This is a mainframe emulator, which is more funny now. This was the holiday last year, and I was busily spending a lot of the holiday testing out mitigations for these side channel attacks on various architectures, not just x86, which everyone knows and loves, but also all the ARM architectures, all the IBM architectures. I think there were about a dozen different types of computer architecture that we ended up spending our entire holiday taking care of before January. So you're welcome for that. And anyway, how did we get here, right? Let's talk a little bit about that. Fundamentally, we got here because hardware and software people don't talk to each other, right? We actually go out of our way to not talk to each other. If we work in software, we're like, it's just hardware, like it doesn't matter, right? And people who work in hardware are like, those software people, So a lot of the things that we've had this year have come about because the industry has busily spent, the last many decades heavily optimizing machines to make them run faster, and we never asked what happened in return for making it faster, right? We just were happy that we got faster. I mean, I would ask the question, but we'd all lie. So, no one here, if I'd come to you a year ago and said, how many of you would take a machine 30% slower that was safer, right? Now, today, we seriously entertain that, but a lot of these guys had difficulties over the past few years, in having these kind of conversations. So it's actually very useful. But I hope that people, as a takeaway, really come to understand that there is no concept of a hardware or a software person. We are all just people, and we're all great, and we're all in one industry together. And so now is the time to remedy that, especially as the world is changing and Moore's Law is over. Sorry, it's gone, right? So as the world changes, what can we do about it? And this is very important. Right, so what I'm going to do now is I'm going to go through some slides that give you kind of an overview of kind of computer architecture concepts that might be relevant. The slides will be available when I email them, 2 slides at USENIX. Anyway, they will be available, and you can go through them in detail, so I'm not going to read them line by line, okay? Okay, so there's 2 things I want to talk about, architecture and microarchitecture, right? So architecture is basically a set of specifications published by these big name brand companies, Intel, AMD, ARM, IBM. And what the architecture specifications do is they say how compatible computers should behave, right? And if you adhere to those specifications, then you might be compatible with other similar computers, right? That's basically what architecture means. And x86 is, of course, an example that everyone has heard of, but there are others out there as well. It's important that architecture is the lowest level targeted by a programmer, right? Most programmers assume a simple sequential execution of their program. I do this, and then I do this, and then I do this, right? And that's because they read the architecture specification and they draw various assumptions from it. Underneath, other things can happen, but the whole idea is that as long as we behave according to the specification, you won't know the difference. And one of the things we're going to learn today is that that's not always true, okay? Most importantly, ISAs, or computer architectures, traditionally had this timing-independent model, right? They didn't have this awareness of reality. They just had this idea that I do this, and I do this, and I do this, and here are my capabilities. But they didn't factor in the realities of how you might implement that, right? And so within the concept of architecture, we have different pieces of software that implement to these specs. We have application programs, we have operating systems, we also have hypervisors and other pieces, but we're going to focus on applications and operating systems today, right? So applications have this view of the world, right? They have some memory, and they have some registers that they use. These are small local data stores inside the processor where they load values and perform calculations. And when you compile your program, it is targeting the ISA spec, and it is going to use registers in the CPU. That's what your compiler is doing, and it's going to use memory. And programs execute within what's called a virtual memory environment. So that means that every program has this handy-dandy notion that it has the entire memory to itself. These days, this is different from decades ago, but these days, programs don't have to have explicit awareness of, what memory is every other program using, and how do I fit in with that. Now, at a very high performance level, I'm sure our friends at Netflix do have to worry about some of these things, and others here do have to worry about this, but at a basic level, we made it boring. We created these abstractions so that every program thinks it's the only thing running on the machine. And we have hardware that helps us with this. So we have a memory management unit, and its job is to provide this abstraction for us. Okay? Now, it's a bit more complicated, because what used to happen, and I'll come back to this later, but what used to happen is Linux and other operating systems have further optimizations. They said, well, every program running on the machine is going to get this view of memory, but what I'm going to do is I'm going to divide it. I'm going to put your program in the bottom part of memory, and I'm going to keep the top part, the addresses that are high in my memory, for my operating system. But I'm going to use a little trick in my hardware, in my memory management unit, so that normal applications can't even tell that I'm keeping this little range for myself. Okay? Just think about that for a minute. We'll come back to it. There'll be a test at the end. Operating systems use a different set of instructions in our architecture. They have additional privileged operations they can use, and the goal there is to lie to all of us and provide this nice, handy view that, the machine is just theirs for this one application, right? And we have all kinds of interfaces that operating systems use to maintain this illusion, right? I'm going to keep going. So examples of computer architectures. Again, actually, I don't have the IBM one yet. I'll come back to that. So examples of architectures, Intel x86, everyone's heard of. If you have a cell phone in your pocket, probably it's ARM-based, right? 95% confidence it's ARM-based. 95% confidence your laptop is x86 today, right? And, we can compare different architecture features, but fundamentally, they're very similar. Computer microarchitecture. So microarchitecture is what people like me get overly excited about, and until this year, not many other people. So it's kind of been fun this year, like, hey, who's a microarchitecture nerd? Ooh, more people. Not just one. That's cool. So we'll talk a little bit about hardware, but then don't worry, we'll stop talking about hardware, right? So, you know, modern chips that you have in your servers or in your computers, they're actually often called system on chips. They do more than one thing. They have lots of pieces on them. They have processors, right? So we loosely use that term, especially in the software space. By processor, we normally mean cores, and we typically subdivide those cores into threads, right? We'll come back to what these mean in a minute. But at a hardware level, we have this chip. It has a whole bunch of pins coming off it, you know, thousands of little pins on it that bring out all these I/Os, all these interfaces to external components. And on the chip, we have cores and we have caches. We have other stuff too, but for today's purpose, we're going to talk about cores that do the compute and caches that bring memory. We've got these big memory chips next to our processors, very expensive these days. Prices are going up all the time, right? These memory chips contain most of what we want, but we can't use that directly. We have to bring that memory into the core. We have to bring it close to where the compute happens. And so as we perform operations, what's happening is memory is coming in through our cache hierarchy. It's getting closer to our cores. And when it reaches what's called the level 1, the closest to the core, that's where we're actually using the data that we want to operate on, right? We'll come back to it a bit later, but one of the things this means is that caching is all about bringing data closer to where I need it. These caches are not infinitely large. In fact, they're quite small. A level 1 cache might be 32 kilobytes, right? That's barely enough for a tenth of a cat photo, right? So what's happening is, you can imagine, data's coming in all the time. It's getting replaced all the time, right? We have caches are simply copies, fast copies of what's in memory, right? So we're not removing things from memory, but what we're doing is we're trying to bring it in, we're trying to keep a copy local to us, and as we use other data, we are displacing the values that we have cached, and we're trying to keep close to us whatever we're working on right now, right? As a consequence, we might be able to measure the difference in the time it takes to access something in order to determine whether we've cached it or not, right? It gets more exciting, right? Don't worry, we won't go too detailed here, but you know, processors are connected to each other. Normally, if you buy a server, it's a 2-socket machine. That means you have 2 chips, right? They have this thing called coherency, which means that these caches are kept in sync between the processors. There's something called a coherency protocol that handles that underneath. And you can read the slide later for more on that. So microarchitecture refers to a specific implementation of an architecture, right? So I can have a whole family of x86 class laptops with different performance characteristics, but they're still x86. That's the whole thing, okay? And then I can make particular choices about how I implement that. Some of them could be what we call in order. Some of them could be out of order machines. So elements of an in order machine. A simple in order machine is what you might learn first in a computer science class, right? What an in order machine does is exactly what you would imagine sort of conceptually happens when you run a program. You do one thing, then the next thing, the next thing, right? In order cores are very simple. My Fitbit has a little microcontroller in it. It's using an in order core. These are very simple to implement. They're very low power, but they're not very high performance. That's the trade-off, right? They do one thing after another. And you know, you can see the stages here. So we pull data, we pull an instruction in. The first stage there, it says instruction fetch. We work out what that instruction does. We then do that instruction. Maybe we access some memory, and then we complete that instruction. And then we go back and we do the next thing, right? It's very, very sequential. It's not too magic. We have problems with in-order designs. So if you look at the right-hand side here, you see we've got multiple instructions in flight. We've got instruction fetch, instruction decode, execute, etc. And then we've got another instruction coming in. And there's some efficiency we can get by overlapping these stages, but we only ever really get maximum performance in these very rare cases, right? So there's limited ability in an in-order design to hide latencies and to get performance. That's why no one does that in servers and high-performance machines. Out-of-order machines. So an out-of-order machine says, I can do better, right? What it does is it says, if I have a piece of code, if I have a program, and my program loads two things and adds them together. So you see the top on the left there, load A, load B, add them together. And the bottom loads two values, adds them together. Those are independent operations. An in-order machine might go through them in sequence. An out-of-order machine can determine that there's no dependency between these two. I can do that in whatever order I like, as long as the programmer can't tell the difference. And that's the key piece, as long as the programmer cannot tell the difference. So a gentleman by the name of Robert Tomasulo from IBM, as it turns out, invented an algorithm many decades ago called Tomasulo's algorithm. And what it does is it makes this work. It's the magic that we use in most machines we have today. So we take every instruction we want to execute, we put it into what's called a reorder buffer inside our processor, and we resolve what the dependencies are between different instructions. We keep track of them all, and what we can do is we can actually run any of those instructions the moment that one of its dependencies is satisfied. I don't have to wait. I can execute that second block of code the moment I have those two values ready to go. And the reason we do all this is that instructions take different amounts of time. So those two loads there could take very long amounts of time because they're trying to get data from external memory chips. That could take a lot longer than, say, putting one into a local piece of storage and adding two numbers together. So we do this reordering. It's called a reorder buffer. That's how we actually do this underneath. So again, I'll let you read through this a bit more, but elements of an out-of-order core, it's a lot more exciting. If you're really keen to understand the details of out-of-order, you can go to wikichip.org and you can get nice schematics for most of the high-performance processors out there, pipelines, and how they work, right? But we do a lot of fancy stuff. We rename, we reorder instructions, we carefully keep track of them. And again, we divide our processing into two stages. The first part of it is still in order. We go through our program, one instruction after another. We then have this out-of-order backend that actually does the execution, maybe in a completely different order from what you wrote or what the programmer wrote. And then we retire or complete instructions in order. So the idea is that the programmer can never tell that we did this little trick. Okay, I'm going to skip that slide. So summary, microarchitecture refers to a specific implementation. We can ask questions about implementations of architecture, right? How many instructions can I have that are out of order at a time? These are different questions I can ask about a design. But the design engineer is free to do many things as long as they adhere to that architecture specification. And examples of microarchitectures, a specific Intel x86 and a specific IBM Power 8 processor, right? These are specific implementations of those architectures. So let's talk about branch prediction and speculation. So modern processors, they run your program, right? In order to get efficiency, what they want to do is they want to guess ahead of time when they hit conditional statements, if this, do that, otherwise do this other thing. They want to try to guess ahead of time which way those branches are going to go. And this is because we don't want to wait around, right? We don't want to, for example, if I have a conditional if some value, right? That some value might not be available to me immediately. I might have to wait to get that from much slower memory. And the memory in our machines is running much slower than the processor. Processor's running at 3 gigahertz. Your memory's not running at that kind of speed, right? So rather than sit around for an eternity to wait to find out what that if resolves to, I'm going to guess, right? If I guess really well, I can run ahead in the program and I can get efficiency. But what I have to do is I have to keep track of every guess I make and make sure I can undo it later if I was wrong. But the idea is you don't see this, right? So applications typically, every few instructions, will have some statement, if this, do that, right? Very common. Control flow, it's called. And again, rather than wait for that branch to resolve, we want to predict the outcome, and we want to try to be as fast as we can. So we have this concept of speculative execution. What speculation does is it adds an extra column to my previous reorder buffer, and it says, I'm going to run these instructions here. Okay, the first 3, they're done. They've executed. The next 3, I don't know. That statement there, if R1 is 0, I don't yet know if that's true. So what I'm going to do is I'm going to guess that it is, right? And I'm going to keep going and keep running through this program and keep executing as if that were true. But now I have to go purple, right? It's not just because it's blue and red mixed, but it's also, I have to go purple here because what I have to do is I have to keep track of which instructions I have guessed I'm going to execute. I can't commit to that until I find out if that if statement is true. And I'm still waiting for that to finish at the same time. So speculation builds on out-of-order execution. They're very tightly coupled. Instructions are tagged to say this might not complete. This may not be a real instruction. As a consequence, they can't have an architecturally visible effect. What does that mean? Well, if you write a program and you do a divide by 0, what happens? It crashes, right? Or you get an exception. If I do a divide by 0 and it's speculative, I can't do anything about it, right? Because I don't know if I actually am executing that code or not, right? So I can't tell you did something bad until I decide that you actually did that. So in addition to tracking the future, I also have to track whether I'm going to tell you did something bad, but I can't tell you did something bad until I know if you did something bad, right? So, as I said, if the prediction is correct, then as these instructions complete, we're going to say, great, we're done. If we're incorrect, we have to go back to our diagram here. I have to throw away the last 3, right? And the whole thing is, if I'm really clever about how I implement this, I can get a performance speed up because otherwise I'd be sitting there just waiting, right? And I'm really fast at throwing away things I didn't mean to do. I'm running at 3 gigahertz. I can throw away stuff pretty quickly, right? Different kinds of branches. You can have a conditional branch, a simple directional branch, which is basically, if this, go that way, otherwise go this other way. A simple loop would be an example. Go do this, do this, do this, go back to the beginning. That's a simple directional branch at the end, right? Do I have to repeat this loop, yes or no? And what we do is we have predictors to make this better because we can't, we can't just randomly guess, right? If we're always wrong about our predictions, we're going to get much slower. The whole point here is we want to be really good at our predictions so we can save wasting time, right? So we have these really good branch predictors. They're really good. They're like 99% effective at guessing which way branches are going to go. And they keep these histories. You see at the bottom? Taken, taken, not, taken, taken, not. That's an example of a branch history, right? Did we take it last time? Did we not take it? Was it true or false? And we keep track of a certain amount of history inside our machine. You don't see any of this. It's doing all this underneath you. So the reason is branch behavior is rarely random. There's a whole discipline that studies this. But like I said, very, very effective predictors can be created. And modern designs combine a mix of different predictors, right? That's the whole thing. We have all kinds of predictors, not just the one I showed you. We have things called indirect predictors we'll talk more about as well. All kinds of predictors underneath us. Indirect prediction might be something like a function pointer or a virtual method if you're a C++ programmer. I don't know where I'm going to jump to. I'm just going to run this function over here. I don't know, right? It's some function pointer. It's something I don't know until I run it. But we also have predictors that are very good at guessing that as well, right? We've spent decades building amazing hardware that can guess all kinds of things. I'm going to skip that one. So modern processors do all these things because they want to give you a faster performance, right? It's now realized that certain side effects of this may be observable. Talk about virtual memory a little bit more. So I mentioned before that applications have this view that they have the whole machine to themselves. We have a well-defined interface between an application and the operating system through which the application asks the OS for things that it needs. Applications run in this own separate address space. They ask the operating system whenever they want to do something, and the operating system does it for them. Here's a view of memory that an application might have, right? It thinks it has the whole machine to itself. Actually, it doesn't. We have some memory here that the operating system is living in at the high end of the memory that the application sees. And we reserve that for some special things that we do. Or we used to, right? We'll come back to why we don't do that anymore. Virtual memory underneath, what's happening is every application has its own view of memory. It's mapped to real physical memory using things called page tables. We actually have a cache inside the processor that keeps track of page tables as well, because again, we're trying to always make things better. So every time we have to look up, when I access this memory address, where is it really? That takes some time. It takes some time to go and look that up in the hardware, so we have a little cache that keeps track of this as well. But that's just another form of cache, and we'll come back to how we can attack that. It's a complicated process. Every time we access a memory address in our program, by which it is translated into the underlying physical address, there's a thing called a page table walk, which means we have to go through many different stages in our hardware just to load one value. It's crazy what happens underneath. And we've got lots of caches there too. In the case of a hypervisor, we might have to do this twice. We have a virtual machine running your application inside a guest operating system. It sees a view of memory that's translated to physical memory, but wait, that physical memory isn't real. It's memory on the host machine, so it gets translated again, right? You can imagine this gets pretty crazy. Okay, so virtual memory is an interesting idea. It gives us this illusion. We have all these things that help us in the hardware to provide these lies. We also have caches in our processors, as I said. So this is how a cache would be designed. I think I'll probably let you read through this later on, but this talks about how we actually load data into our caches and the policy we use to remove it or replace it with other data. Caches are normally what's called virtually indexed, which means they use the addresses as seen by the program. That's important in a minute. And there's an optimization we can use where we look data up in our cache at the same time that we're also translating what that address is. So some of our caches are actually designed so they're half using the address that the application sees, and they're half using the real one underneath. Right? Again, there's all kinds of optimizations happening. I'll let you read the summary slide later on. Another summary slide. Okay, let's talk about side channel attacks. So what is a side channel attack? A side channel attack is basically any way that we can monitor a computer system, an electrical system, and infer what it's doing, without necessarily, running overtly malicious code. We can monitor something and infer what it's doing. And examples include, taking your bank card and measuring how it's using the electrical voltages on your bank card as you do a transaction. You can actually recover information. If it's got this voltage here, maybe it's doing this, right? People do all kinds of side channel analysis. Cache side channels are just one form. We're going to talk about those, though. So again, caches exist because they make our life faster. They make our machines faster and better and easier to use. The problem with that is that we might be able to measure how that cache is behaving and use that to understand what's going on underneath. So for example, what I can do is I can time the amount of time it takes to access some piece of data, and depending upon how long that takes, I can determine whether that was in the cache or not. And most processors provide us with very convenient means to do this, right? They have nice instructions that will tell us exactly how long it took to do something. It's optimized to make this easy. And it's a big problem because, again, we built everything from a timing-independent view of the world, and now we've realized that time actually matters very much to us. We have ways we can actually intentionally pull things into caches, too. Some processors provide nice, handy ways I can say, oh, I'd really like you to pull this in, right? So they even give us little tricks to help us exploit them. So how does that build into all the attacks that you've seen this year? Again, here's a long list of vulnerabilities. I won't go through every single one, but I'm going to go through a few of them now in the 10 minutes remaining. Again, with all these, we were under a specific timeline, right? That's good, because we don't want to take forever and keep something secret from the world. But a few of us had our vacations ruined last holiday. I had a girlfriend who's very understanding. She got me a Spectre Meltdown vulnerability fighting cape for Valentine's Day. I will have it on for Halloween. She's great, but she was very unhappy when we were in Paris, and I was on the phone talking about this outside while she was eating lunch by herself. Anyway, so we set up a team internal to Red Hat called the Omega team last year. Hands up if you've ever heard of Star Trek, right? It's the Omega Directive, right? It's not allowed to exist. It's a secret, right? That's the reason it was called that. I thought it was funny. But we did a lot of work. We had to do 15 kernel backports going many years. Other vendors did lots of things too. It's not just us. We're great. Everyone's great. We all did a lot of work. We also had to make a lot of materials to help people with these. And it took 10,000 hours. Right? So what we're doing is we're using a combination of interfaces our processors give us. Our processors have some ability to mitigate or address issues in field, and we have the ability to patch software. So we have to use a combination of these two things. That's all we have. We can't go out there and replace all the chips. We just have a combination of things that we can do, right? So when you have deployed your vulnerability mitigations, you can go into Linux and see this ever-growing directory of new things that are exciting every week, and it will tell you how we fixed it. And then you can go and Google and find out what that means. So let's do them one at a time. Meltdown. Meltdown happens when we do a classical Tomasulo algorithm, a typical out-of-order machine, and we track bad things we did, but we don't handle them immediately. We just say, I'll get back to that, right? So I can have some code which loads some data I shouldn't be able to access, okay? Does something with it, generates some other address, and then accesses that other address. And what should happen is I shouldn't be able to load that first address. It's a privileged piece of information. But because the processor is running ahead and speculating, it will for a brief time do this. Now, the second location it accesses is something I control. And by doing a cache timing analysis, I can see if that is in the cache or not, and I can infer, therefore, the content of the memory location I wanted to read. So again, I load something I shouldn't, I do something based on it, and then I access something else. And what I'm going to do is I'm going to measure the something else to see if it was a 0 or 1. I'm going to very slowly capture what the value was. So we'll go through this. I access one location or another. I use that to determine the content I want to read. Right? I'll let you go through this in detail. Here's what happens in the reorder buffer. Something bad happens. I say I should handle this later. I really should. I really should stop speculating here, but I'm going to keep going. And then a really bad thing happens because now I've given away the secrets and there's nothing that can be done anymore. So this happens when you separate privilege checking from actually doing the operation. It's an optimization that these companies have done. When they do it this way, you can perform a meltdown attack. How do we fix meltdown? Well, you can either prevent the data being there, you can either make sure the data's not there to read, or you can make sure that there's no valid translation for it. So what we did in Linux is something called page table isolation. We separate the view of memory the kernel, the OS has, from the view that the application has. It makes your machine slower, but it works. There's some constraints. It gets better on newer hardware. It's much, much more ugly on older hardware. Spectre is about abusing what we call gadgets. So a gadget is a piece of code that is going to abuse speculative execution. It's going to try to access some memory location, and it's going to let us read a piece of data beyond that. What gadgets are doing, gadgets are pieces of code already in an existing program. They're not created, they're not made by a malicious attacker. I'm taking advantage of code that's already there. And what I do in Spectre variant 1 and variant 2 is I mistrain the branch predictors in my machine by running normal code that looks like it's doing one thing, but because this branch predictor is shared between different applications, I can fool it so that later it's going to misexecute or mispredict other execution. And by finding the right piece of code that touches the cache in just the right way, I can then derive information that I should not. So we mitigate Spectre by basically limiting the amount of speculation we can do. I can put little instructions here to stop speculation, or I can be a bit more clever, and I can use something called a clamp to safely force the speculation to a safe value. I'm going to keep going because I'm running low on time. Actually. Okay, there's an optimization for mitigating Spectre v2 called reppolines. You guys can read more about it. Google's amazing. They actually came up with this and donated it to the world, which is great for them. It's a much more performant software mitigation for Spectre. Okay. We have other variants on a theme. We can do a meltdown attack where we can read system information we shouldn't be able to read. That's called variant 3A. We have variant 4. Variant 4 is about abusing the fact that accesses to memory take time, and that I run them through these things called load store queues. And I can actually try to see ahead of time. When I load a piece of data from memory, I'm going to pull it in through this whole infrastructure. And what I'm going to do is, when I load it in, I'm going to want to see if I did a recent store, if I recently wrote to that memory location. But I'm going to guess that I didn't, and I'm going to keep going. And if I was wrong, I'm going to have to fix it later. But again, I might be able to abuse that small piece of time during that speculation to do bad things. So variant 4 was awful. We had another one, lazy floating point. Similar thing with my floating point calculations. I'm going to guess when I switch from one application to another that I'm not going to do any floating point calculations. I'm going to turn off the floating point unit. I'm going to wait until the next application uses it. But that next application could be malicious, and there's a means it can use to determine the floating point or vector activity of the previous application. There's another variant of Spectre, a store variant. There's an attack on TLBs, on these caches that translate memory addresses. They're everywhere. And I'm going to do two more. There's one called NetSpectre, which is Spectre over the network. This is when you attack a machine remotely using Spectre, which is particularly bad. And then my final one, in closing, is L1 terminal fault, which came out pretty recently. L1 terminal fault is particularly bad because it can be used to attack virtual machines. So, as I said, we do these memory translations inside VMs. As an optimization, what I do inside my processor is I guess whether my translations are valid or not, and I keep moving. But unfortunately, during that process, I could briefly access memory to which I shouldn't be permitted access. And in the case of Intel machines that were vulnerable, they would do the first stage translation inside a VM, and they would stop there. So rather than take that address and do a second stage translation, there's a means to attack it where you can take the first stage, force it to end early, and then treat that address as a real memory address on the host machine and read memory to which you're not entitled. So foreshadow is particularly awful. We have means to mitigate it, but that's also very bad. Some related research in closing. Meltdown and Spectre are just examples of attacks. I've tried to give you a speed walkthrough of some of the issues here. I will be available for questions, and I'd like to engage you with this. But I want you to understand that this is just the latest iteration of computer security issues affecting hardware. There are many more. There are some that attack physically aged silicon, by running bad code. So where do we go from here? Well, we obviously need to change how we design hardware, right? That's key. We have to build new processors that are all fixed now. But we also need to change how we operate as a community so that we understand that our hardware friends are just trying to make machines faster for us, and we need to work together as one community. Open source can help, right? There are open source computer architectures like RISC-V, but just because something's open source doesn't always make it, just magically better. It only gets better if we collaborate and work around that. So I encourage people who are interested in architecture, in how these machines work, go take a look at things like RISC-V. You can actually download processor designs and play with them on your laptop, and you can understand how these machines really work inside. And with that, I'd like to thank you very much for your time.